This is Floss Weekly. I'm Doc Searls. This week, Jonathan Bennett and I are talking with Stephano Cetola about RISC-V. He was with us a little over a year ago, and so much has happened since then, and so much of it is exciting that you really need to get this one. There are things being done with RISC-V that aren't happening with ARM. They're not happening with other CPU designs. They are really cool and really portentous, and that is coming up next.
Podcasts you love.
From people you trust.
This is TWiT.
This is Floss Weekly, episode 690, recorded Wednesday, July 20th, 2022. RISC-V Revisited. This episode of Floss Weekly is brought to you by Collide. That's Collide with a K. Collide is an endpoint security solution built around honest security. You can meet your security goals without compromising your values. Visit collide.com/floss to learn more and activate a free 14-day trial today. No credit card required. Hello again, everybody everywhere. I am Doc Searls, and this is Floss Weekly. I'm joined this week by Jonathan Bennett, he's got his new haircut, and he's looking all cool. There he is.
Hey, Doc.
What's the background there? Is a giant screen in front of a man cave wall sort of looking thing?
Something like that. It's the built-in desk behind me and then a couple of monitors, but I've got a polarizing filter on the camera turned just right so you can't see what's on my monitors.
Cool. that's very cool. Yeah, I in my car I have I have an old car, so I don't have like the built-in screen in the dashboard. I just have a phone that's clamped onto the thing that you shove into the CD slot because who does CDs anymore? And that didn't work anyway. And I always wear Polaroid sunglasses, but I can only see the phone if I twist it sideways. That's the deal. Or
tilt your head to the side as you're driving down the road.
No, drive like this. Yeah. New thing. So just to cut down the reflection on you, you've got the leather chair there that makes you look shorter than you really are, and that's reflective also. But you're not worried about the reflection; just worried about what's on the screen.
Yeah, once upon a time, I was always very careful before the show. It's like, all right, let's put Hackaday up on one side and maybe the TWiT logo on the other. And I always had this fear that I'm going to forget and accidentally leave, a document up that I don't need the world to see, something like that. And eventually I just concluded, I've got this polarizing filter. I can just take care of it. And so I've done that ever since.
You don't have the you have been summoned to appear. None of those.
No, I mean, I manage IT for a lot of different businesses, and so I've got documents with their secrets on it and stuff. So I try to be real careful about that. So anyway,
so our guest today is Stephano Cetola, who we had on a little over a year ago, and you actually volunteered. You came forward saying, "I want to be on this show," which we don't usually get.
Well, it was just such a great conversation last time. I was excited to come back and do it again.
There he is. Yeah. So I might as well introduce you because we didn't start with an ad. So I'm just so Stephano, for those of you who are visually enabled, just saw come on, is the director of technical programs for RISC-V International. He's developed and managed numerous open source initiatives in software and hardware over the course of his 20-year career in technology. Before that, he worked for Intel, contributing to the Yocto project, embedded Linux and various open source firmware efforts. So welcome to the show, dude. He's back.
Thank you. Thanks, Doc. So it's great to be back.
Yeah. So why don't we just start by filling us in on what's going on for the last year or so? I mean, what's different this time? Because one reason we have you on is because it is different. Things are going on.
Yeah. One of the reasons why I reached out was because we had a lot of work that got done last year, and so it's exciting to see the RISC-V community growing. It's exciting to see a lot of stuff getting done, and so I just wanted to come and chat about some of it. I wanted to start by talking about some of the extensions that we've ratified, but before I do that, let me pull back a little bit for your audience. For those who are relatively new to RISC-V. RISC-V is an open source ISA and instruction set architecture. I'm going to talk a little bit about some extensions that we've ratified, but before I do that, I should probably talk about why we care about extensions. So the RISC-V ISA, like I said, it's open source, so opposed to Intel's x86 and ARM's architecture. This one is developed in a community setting, in an open source setting. And the base of the ISA is essentially the groundwork for a processor. So you've got, as an example, RV32I is the 32-bit integer base ISA. And this gives you things like 32-bit. It tells you whether it's 32-bit, 64-bit, 128-bit. It gives you the register layout. So for the integer, there's 32 registers. It describes how operations are done. So what do the opcodes look like? And how would one do an AND or an OR? So that's essentially the foundation for RISC-V. But then on top of it, we layer extensions that do useful things. So things like multiplication with the M extension, or floating point with F and D. So what you can imagine is this base ISA has several extensions layered on top of it to allow you to do something even more useful than a calculator, like boot Linux. So you get enough extensions piled on top and you can actually boot Linux. And the beauty behind the standardization of these extensions is, as you might imagine, if we don't standardize around multiplication, everyone's going to go off and do it their own way. Now, with multiplication, that might not be such an issue, but when you start to get into the more complex things I'm going to talk about, like vector or cryptography, we really want the community aligned behind specific standard extensions. That way, we reduce the effort. The community gets to work on it, we release one version of it, and everyone can build their value add on top of that. Now, that being said, we don't discourage custom extensions. So if you wanted to go off and write some, fancy extension that doesn't standardize and isn't common throughout RISC-V's ecosystem, you can absolutely do that. We reserve opcode space specifically for that to happen. So that's essentially the concept behind why we have extensions, and the power is really in the flexibility, right? When you're building a microprocessor or a larger, enterprise level chip, you get to pick and choose which extensions you're going to add. And this is much different than in the traditional setup we have today, where if you buy a platform, you're already getting all the stuff. Regardless of whether or not you're planning to use Vector, Vector's already on your chip. So I mentioned Vector a couple of times. That's one that we ratified. A lot of folks have been looking forward to this one. It's actually been frozen. It was frozen for quite a while, so we had plenty of time for the community to review it, but we just recently ratified it in December. The idea behind Vector, for those who aren't familiar with vector processing, it's a type of parallel processing. The concept has been around since the 60s, and we use parallel processing in our daily life all the time. Your phone has tons of cores in it. Your desktop has even more cores in it. That's one type of parallel processing. Vector is a different type, which uses multiple different pieces of data to operate on the same instruction. What that all translates to in practice, one of the common examples, there's things like graphics. You can imagine on your screen, there's a whole bunch of pixels, and they're set up in a grid fashion. And you may want to perform some operation, some instruction on those pixels, but you may want to do it to more than one pixel. So you might want to do it to a whole row or to several rows. With a traditional processor, a traditional core, you're going to line up those instructions in each of those pixels, and one at a time, you're going to loop through them. And if you're particularly smart, you're going to spin up 8 cores, and you're going to do 8 of them at a time. But there's an inherent limit to what you can do there. You're limited by the number of cores. With vector processing, you're allowed to create special registers and special instructions that then act on multiple different pieces of data. So you can change, say, the pixels in your entire screen or in a set of rows would be the analogy. And there are multiple other places you might want to do this sort of computation. Graphics is just a common one that people use, but there's also machine learning, artificial intelligence, lots of different aspects of computing where multiple data being operated on the same time is critical. So that's one of the extensions that we ratified that lots of folks are excited about. As you imagine with graphics, you're going to start to see this come into play with things like graphics cards, which we all care about, but then also in things like neural network processing. So when you hold your phone up to your face to open it, it would be really nice if that didn't take 35 seconds. So that's one of the things that Vector gets us, is the ability to put our hand down quicker.
Hey, I'm curious about this. Before we go on to the next one, I've got to ask. This almost seems like this is being implemented in RISC-V differently than some of the other platforms. So, for example, you mentioned cell phones. So, our cell phones, they have an ARM chip, and then sometimes it's on the silicon, sometimes it's a separate chip. But there'll be, say, a Power VR, whether it's physical or logical. It's a discrete device. The way you're describing these vector extensions, it almost sounds like you're taking the GPU stuff and actually making it part of the CPU proper. Is that kind of a different approach than any of the other chip designs have gone with?
The approach is different in a subtle way. Excuse me. It's a little different than that, but let me touch on what you're getting at. So what you're getting at is with RISC-V, we've called out these extensions. So it's very obvious. Here's the part of the processor that's doing your traditional compute. Here's the part that's doing vector. And we're doing that in a very obvious way. Other chip manufacturers historically have done it, but have done it in a much more subtle way. So it's hard for you to know, is there vector processing on my chip, or is it its own accelerator? The answer is most of the time it's both. Most of the time there is a part of that silicon that has some vector processing capability, but whether or not they want to talk about it is up to the person manufacturing that chip. What they will likely talk about is their accelerator that they put on there. So when they want to sell you a phone, they're going to tell you that they have a fancy accelerator that's, maybe on a special bus connected to the chip that's going to do neural network processing or image processing in an extra quick manner. So RISC-V isn't doing it differently that way, in that we're just being much more transparent. So we're saying, here's our vector extension that's separate from the base ISA, and here's how you could implement it. And then we leave it up to the implementers, the folks actually making the chips, to say, okay, well, I'm just interested in creating an image processing accelerator. So maybe I want a very simple core. Like I was saying, the base ISA has several extensions you could layer on top, but you can keep it very small. So maybe a very small RISC-V core, and then connect that to a specialized unit for doing vector processing. And that piece of silicon would be considered an accelerator. And the beauty of RISC-V is that this is all very transparent. You're able to look at the specification and see how people are actually creating things. Even if they don't open up the source to you, you can still get an idea for what they're doing. Does that make sense?
So it does. So someone could take the RISC-V ISA and build a dedicated GPU out of it. Now, obviously, we're kind of heading in the clouds with this idea, but it sounds like that's a possibility.
Absolutely. And it's not that far off. I mean, if you think about it, if you're out there building SoCs today and you're using RISC-V, you are most likely doing graphics processing. So there's going to be some graphics capability to that chip. And the chances are that you're offloading, the amount of work you need. So if you're doing general purpose compute, you need a decent amount of graphics computational power there. The idea that someone's out there creating a dedicated GPU is a big step, but the groundwork is already laid for that. So it's not that far-fetched.
Yeah, very interesting. All right, I'm sure you want to talk about some of the other extensions. I see on our notes here that there are also cryptographic extensions, which have a lot of potential in different places. Why don't we talk about that?
Indeed. Yeah. No, we're excited about the crypto. So we did crypto scalar. So scalar you could think of as, just to simplify it down, we have scalar operations and vector operations. That's a gross oversimplification. So my apologies to those out there who actually study vector processing. But the idea is for crypto, we started with the scalar operations that are very common. So you can think of SHA-256, AES, the algorithms that you're used to hearing. Even if you don't know what they are, you hear about them because you use them every day. You use them every time you type HTTPS into your browser, assuming you're actually doing that. These cryptographic algorithms underpin everything we do in computing. We can't do anything in computing without them. The key is we're standardizing around them. And that's why the extension is important. It's not so important in that it's doing something wildly different, or it's certainly not doing anything that cryptography scholars are going to dig into. What it does is it enables cryptography scholars, people who are doing security research, to layer their ideas on top of a standard and not have to worry about that standard changing in the future. So they know that those algorithms, those instructions are going to be available to them going forward. And it also opens up the door to more interesting things.
You kind of want your cryptography implementation to be real boring as much as possible.
Exactly. Yeah. No, that is kind of the saying. You want it to be boring. You don't want it to be terribly exciting. And that gets, it's funny, that term gets bandied around a lot, because if you look at it from a software perspective, they don't want it to be terribly interesting. 9 times out of 10, they want it to be boring. They want to be able to compile their code and run it on your machine, just like they've been running their software on machines for the past 50 years. They don't want to change the way they're doing things. So a lot of our stuff, I don't want to say it's just coming up to parity, but what it's doing is it's bringing the cryptography capabilities that software developers want and standardizing that and making it readily available. And it's opening the door to what we want to do next, which is things like vector cryptography. So more interesting extensions that do provide advanced features. But again, giving folks the option of whether or not they want to implement that in their product. So not saying it's part of the base ISA. It's not something they have to do. It's an option. It gives them that flexibility to do it or not to do it.
I'm curious, and we're gonna get into the weeds here for just a moment. I'm real curious though about how, and I would have to really look into how the documentation of this works. But so you mentioned SHA-256, and I don't know what the primitives look like, but I'm curious. So SHA-256 at this point is just about old crypto, and NIST, a couple of weeks ago just said, hey, we are now ratifying, we have selected some post-quantum crypto, right, which have some real fun geeky names like Crystals Kyber and Crystals Dilithium. There's some real sci-fi geeks in some of those groups.
They're getting creative.
What is what does the path look like to making those next gen crypto algorithms work in RISC-V? Are the primitives that you've implemented in these crypto extensions, are they basic and flexible enough that it's just a matter of writing the code and hooking it up to the extensions, or is this going to have to be another round of extensions to support the next, kind of the next ideas in crypto?
Yeah, no, so you sort of hit on it when you use the term implemented. So what we've implemented is really just a framework. So it's not here's how you're going to build your algorithm. Here's the pieces you're going to put together. It's just the requirement for here's what instruction we expect to be there, and here's how that instruction should work. Now you go off and implement your SHA-256 or SHA-512 or your next generation algorithm, however you want to integrate it or implement it. We're just telling you here's the standard way that people are going to expect to be able to communicate to the processor. So here's the instruction they're going to use. So getting to your point of how do we layer on top of that? So we have scalar crypto instructions today that create a base, a foundation for folks to build on. We'll add to those in the coming year with vector crypto. And your concept of, where do we go with the really future looking stuff, the quantum stuff, that's where RISC-V's flexibility really comes in handy, because now we have a community that's willing to align around, which of these futuristic, for lack of a better term, algorithms are we interested in standardizing around? But where do we want to stay away from to allow the industry to create innovative solutions that aren't standards, that are their custom instructions? Because if you think about it from a value add perspective, as we move up that stack of cryptography closer to cutting edge, we're getting at the value add, right? RISC-V wants to be simple. It wants to be basic so that companies can come in and innovate at that top level and do some really interesting quantum stuff. And then hopefully the community can look at what's going on and decide which pieces of that they want to start standardizing. But there's no reason we have to standardize the stuff that's really cutting edge.
And I'm sure there's kind of a flowdown where some of these things at various companies, because we see this in other places in the tech industry, AMD or Intel or NVIDIA, whoever, they do something really, really clever, and it's just on their stuff for the first couple of years. And then the next thing you know, that's been folded into the standard. And now, right, you buy the next generation of chip and everybody has it. Do you see that kind of flow down happen with RISC as well, where some of these extensions that start out as custom just from one company, the next thing you know, they're getting folded in officially?
Yeah, absolutely. Yeah, you can already sort of see that happening today. So the way RISC-V is structured as a nonprofit is you have members who are, at different levels at the organization. And you'll notice that the companies that are sort of driving innovation, the ones who are premier members, are the ones that are slowly integrating some of the big new concepts. So things like Pact SIMD is a good example. We have a group from Andy's technology that have clearly already implemented this, but they're trying to figure out, okay, how do we take the stuff that we have implemented and bring some of that into a standard? Because at the end of the day, that rising tide is going to lift all the boats, and RISC-V will do better, and we'll still have our piece that we can layer on top of that. So you're already starting to see that in vector type processing. I imagine you're going to start seeing it in cryptography, specifically around different security stuff. So I'm thinking about things like OpenTitan that Google did. So that was one of the first areas where folks said, okay, TPMs, trusted platform modules, is something that everyone needs, right? We all, again, when you hold your phone up to your face, it needs a way to compare what it's seeing with some secured image, and that needs to be secured. So we need some trusted platform module to store things like cryptographic keys. But the way in which we're doing that is not something that companies see as their value add. It's much better if we all combine our efforts around that idea of a TPM. Now, if you think a little bit about that TPM today is operating on sort of the traditional computing standards. As we introduce things like quantum, there will be places to innovate, even in a TPM. The question is, as these companies go off and do that, what are they going to find that they think, okay, this is going to be much better to pull down into a standard so that I can work across organizations with Google and with Huawei and with Alibaba to come up with a solution that allows us all to layer on top of it. I think that's what you'll end up seeing is those filters of, we know where we're innovating. What can we bring in and work together as a group on?
Yeah, excellent. I know there is one other sort of extension or group of extensions that you really want to cover, and that's the physical memory protection. And I will probably have some follow-up questions about this because it sounds real fascinating.
Absolutely. Yeah. No, that one's kind of near and dear to me. So trusted execution environments are something that most people have probably run into, whether or not they know it from that acronym. But think about ARM Trust Zone or Intel SGX. So I mentioned earlier, ways in which we log into our phone have advanced. But it even goes further than that. When you're opening up your banking app, there needs to be a way to securely open that application and know that the phone hasn't been tampered with. And so companies have been using trusted execution environments, which are essentially an area of computation that has a higher level of protection. So a way of quarantining off specific operations or specific tasks in an area that's more secure. Now, this is old hat. This has been around a while. SGX and Trust Zone have both been around for over a decade. The beauty of RISC-V is that not only do we get to learn from historically what's happened there, but we get to start from an open standard. And that's what physical memory protection is. It's the first layer in that open standard. So as you might imagine, let's just pick on Trust Zone. Trust Zone is something that lots of chip manufacturers have to implement. And there are lots of layers to Trust Zone. It's not simply one layer of protection. It's actually several layers that the application has to go through to execute its code. All of those layers were defined, and there was you didn't get a say in that. You got handed Trust Zone and told how to implement it, and you get to go implement it. With RISC-V, we're starting with sort of a bottom layer of physical memory protection and layering on top of that until we have a trusted application platform. And all of this is being developed in the open. So physical memory protection is sort of the first layer. You can really just think of it as a way to protect the actual physical hardware memory, almost like a bitmap that sits above that the hardware is able to have control over. And what we ratified in December was the next layer up, sort of an advanced or an enhanced layer of physical memory protection. And we have a security task group that's working on, several different parts of the stack now, and they're just starting work on sort of the application layer. So how does an application that boots through these protected layers of memory then make calls back in to continue execution in a secure environment? And the part that's interesting is that we're all doing this in an open task group that anyone can join, that anyone can contribute to. And it's going to be a completely different model than what we've seen before, simply because it's going to get to learn from past mistakes and take into account the direction that people are trying to go today. If you imagine, 20 years ago when they were looking at this concept, they were doing it for things like chip and pin computations. Completely different than the kind of things we're trying to do in an enclave or in a trusted execution environment today. Today, we're trying to shove huge applications into these trusted zones of computation. So not quite chip and pin simplicity. So I think the thing that we're going to win is the ability to look at something much more holistically and build a solution that's geared toward the problems of today.
Does physical memory protection include things like encrypting memory physically?
So it doesn't, it sort of stays clear of how you want to implement that encryption. So what it does is it gives you a mechanism by which to allow or deny access to the memory. And then the next layer up essentially allows you to run, let's say, an operating system or a hypervisor and make calls back into that securely. So it really is the foundation. It hasn't even gotten up to the point of, okay, how do I encrypt something inside that memory yet? You will see that. There will be instructions, I'm sure, that talk about, all right, let's say I want to store something in the trusted execution environment and I want to encrypt it, and here's where I store my key. That's the sort of problem that we're solving today, is those sort of issues. And how do we standardize that? How do we get everyone to align around specific ways of accomplishing that?
So I've got to ask, how has RISC-V avoided the classic problem of design by committee? Sometimes when you have a bunch of people working on these problems, the solutions end up unwieldy, let's say.
Right. Yeah. No, I was just talking to actually our CTO, Mark, this morning about this. It's all about pushing the responsibility down into the task groups, and then the task groups align around a committee. So that's kind of a complicated answer to the idea of we're not a consensus organization. We're an organization that works with task groups whose job is to get work done. And so if something is standing in the way of getting that work done, it's our job at RISC-V International to solve those issues and to bring those to closure. But because the technical steering committee, the sort of high-level committee that oversees all these task groups, has pushed a lot of the responsibility down into the work group, what you end up is with experts in that field making the decision. So the technical steering committee oversees it. They will get a final say before we ratify a specification. However, they have pushed the decision-making down to the people who know that area of expertise. And while we have populated the technical steering committee with experts, so we make sure that there's someone on there who really understands security, for example, we make sure that there are actually two different folks that understand different ends of software. So software from a sort of operating system level perspective, but also application level software perspectives. These are things that you don't often see in hardware standards bodies. They tend to just leave software to the software folks. But RISC-V is aligning all those folks at sort of that top level committee. But like I said, pushing all the responsibility down for doing the work to the task group and leaving those decisions up to them. Now, the task groups do have to stand by their decisions and give reasons why they made those decisions, but it doesn't become every committee gets its own say and everyone gets to throw in 2 cents. It really ends up being this tight-knit working group of folks who are all aligned around a vision. I would actually pick on the crypto group as a great example of that. If you go to one of the crypto meetings, it's usually somewhere between 10 and 15 cryptography experts meeting to discuss what makes sense in that specification and why. And when they're done with their specification, you can just shy of guarantee that when they hand that to the TSC, it's going to be flawless, or, there'll be a few things that, a few T's need to be crossed or whatnot. But it really is, it's a example of how when you get experts in a room and you work with them to align on a goal, you avoid that problem of, well, the committee each has their own opinion. So you're going to get 20 different opinions. You really end up with a much more cohesive work process.
In this case, the metaphorical committee is made up of engineers instead of middle management.
Right, exactly. Yeah, and we don't completely remove the management. There is still oversight. Companies still have interests, and we want to make sure those interests are we're aware of them and that we take them into account. But we let the engineers do their jobs and come out with a spec that, when you bring that spec to a cryptography conference and talk about it, you can be proud of it, and you can know that you're standing behind a bunch of cryptography experts who think that this is the right way to move forward. I'll also touch on public review. So staying on sort of this cryptography spec, before we ratified it, we put it out for a 45-day public review period on a public mailing list that really gave anyone a chance to comment. So if there's, dissent in the broader community, aside from just RISC-V International and people who are members, but the broader community, and that includes the Linux kernel community and other communities that you can imagine might have a thing or two to say about a RISC-V specification. We give them that opportunity to voice their opinion, and we take that back and discuss that both at the TSC level with the technical steering committee and at the board before we ratify it. So you can be sure that if there is dissent somewhere out there, that dissent is rolling all the way up through our process of ratification and may even change what the spec looks like if the dissent it warrants that sort of conversation.
So I find myself wondering about how users or buyers in the actual world are going to see and touch this. But before we go there, I want to let everybody know that this episode of FLOSS Weekly is brought to us by Collide. IT admins often feel like they have to choose between their commitment to cybersecurity and their duty to protect their employees' privacy. Naturally, you need to safeguard company data against hacks and breaches, but you don't want to turn your workplace into 1984. Traditional MDMs give the IT team complete access and control over company devices, but since employees are inevitably going to use their work laptops for personal activities, these tools can saddle you with surveillance capabilities you never wanted, like access to photos and browser history. So before you know it, the end users are complaining about all the security agents slowing down their laptops. Developers are frustrated by a lack of autonomy. People start secretly working on their personal devices just to get things done. So it's easy to fall into the trap of top-down security, but it's not the only option. Collide is an endpoint security solution built around honest security. Their philosophy is that employees aren't your biggest security risk, they're your biggest allies. And your relationship with them should be based on transparency and informed consent. So Collide works by notifying your employees of security issues via Slack, educating them on why they're important and giving them step-by-step instructions on how to resolve them themselves. For IT and security teams, Collide provides the right level of visibility for Mac, Windows, and Linux devices, and it addresses high-risk issues that can't be solved through brute force or automation. What's more, your end users can see exactly why and how every piece of data is being collected via Collide's User Privacy Center and their open source code base. You can meet your security goals without compromising your values. Visit collide.com/floss and find out how. If you follow that link, they'll hook you up with a goodie bag just for activating a free trial. That's KOLIDE.com/floss. Okay, so as we're looking at the real world here, I mean, I'm fascinated by all the stuff you're working on with the engineers and the companies and all the different groups. But somebody wants to use one of these. I know you've got some stuff coming up. So where do we see this in the real world? Where can you see and touch and hold and buy stuff?
Yeah, that's what it comes down to, is what can I get my hands on and actually boot?
Sooner or later, people buy this stuff, right?
Right. Well, so we've had a lot of interesting stuff happen. Sorry. The past year has been obviously a little rough with the chip shortage. So the chip shortage has affected folks who are ordering in small quantities. And as you might imagine, RISC-V tends to be ordered in small quantities because these are all relatively new efforts. That being said, we have had some really interesting stuff happen. Probably the most pertinent and the one that happened the most recently was the laptop that got announced. So I wanted to sort of touch on it because there's been already a little bit of chatter around, what is this laptop? What's the point of it? So you have to realize with a new architecture, especially one that isn't being, brought to you by Google or brought to you by large corporation XYZ, there's going to be efforts to spin up products that may not be for everybody. So this laptop is a developer laptop, but it's not meant for your average kernel hacker to go compile the kernel on. It's really meant for folks who are currently developing applications and want to natively compile on RISC-V. So it doesn't matter what type of application, the idea being that it's not something that's going to be a workhorse for you as a kernel engineer or as someone working on a large web application to regularly compile your app, but rather for someone who's interested in trying out RISC-V native compile on their app. So as an example, we're already trying to get these laptops in the hands of distro folks from SUSE and from Red Hat and from Ubuntu. We're hoping to get some shipped over to the folks at VMware, other software vendors who we'd like to see them compiling their stuff on RISC-V, because that feedback that we can get from that native compile, even if it's not, in a traditional CI/CD setup, it's not a server that I hand them to put into their server farm and run consistent builds on, it still gives us feedback and is valuable for the community. And so, that's really the goal with this laptop is how do we sort of be a first mover and put a line in the sand of, all right, here's how one might build a laptop. And then what feedback can we get back from that into the community to help folks who are interested in getting involved specifically in software. So getting involved in hardware is pretty straightforward. I'm sure at some point in this interview, there'll be a link to RISC-V's website and you can go join for free and be a member, and we'll happily help you get involved and change how the ISA works and contribute there. Getting involved in software can be much more difficult, especially when you're relying on QEMU, you're relying on some sort of emulation. So actually having a platform in front of you is key. Now we have a lot of developer boards out there. We've got a D1 board that I think is under $100 now. The folks from BeagleBoard actually came out with a prototype. So they were hoping to go to mass production with that. But again, because of the chip shortage and other issues, that was difficult. So hopefully this year or early next year, we'll see sort of the BeagleBoard version 2 for RISC-V. But these smaller developer boards, or I don't want to say smaller, but also more complex FPGA-based boards aren't really ideal for software developers. While the little dev board is great and you can compile stuff on it and play with it, it's not a traditional setup. A laptop is a much more traditional setup that you can sit down on, download your application, compile it, and start debugging. And it also gives us, as RISC-V International, an opportunity to seed the software community with these laptops in order to get feedback for how we're doing. What parts of our tool chain need work? What parts of GCC need work? What pieces of that code are compiling and much, much larger? We need that sort of feedback so that we can do our job.
So in the video version of this show, we just saw a story in Ars Technica that had this phrase in it, silicon replacement, and I never thought about that before, that, wait a minute, because one of the things you imagine is you're never going to replace the CPU. It's like the head. You don't replace the head on somebody, and they're not somebody else. But the idea of replacing a CPU makes complete sense, actually. You should be able to do that. Is that a design or a design feature that came along in the first place, that you want to do silicon replacement as like have modularity go all the way down, right, replaceability go all the way down? That's cool. Yeah.
This is a conversation we have quite a bit in our community. Part of the reason is, and I'll use as an example, a company called Framework. It's frame.work if you want to browse to their website. And I'm not being paid to endorse them. Great people though. And they make some really interesting laptops. The laptops that they make are, by their very nature, serviceable. You can open them up. You can replace the motherboard inside them. You can replace the screen. So this concept of, replacing your processor in your laptop is something that we're really interested in. And now that's twofold. There's two reasons for that. First off, because we know that as RISC-V gets spun up, there are going to be less powerful processors than something you can go buy from Intel. So this first laptop that you buy is not going to be as powerful as the thing you can go grab off the shelf from Lenovo. That's for sure. And so that upgradability, the ability to swap out that CPU, is something that we'd be interested in. And it is sort of what RISC-V is built for, is that modularity, right? So I've been talking a lot about extensions at the beginning. The whole idea that RISC-V can be completely modular means that you can decide what all of your peripherals look like. And so the chip can be completely sort of replaceable. You can sort of remove that module and put it in a different module with a different chip. That's something, that flexibility isn't something that was historically possible, mostly because vendors were sort of locked into different levels of support, right? They were going to sell so many million of these units. They needed to be sure that they could support those units over a certain number of years, and that those units would be replaceable by the next platform, whatever they came out with next. With RISC-V, we're trying to be much more flexible in how people build laptops and build their products. And so the idea that you might have sort of a system on a module that's able to be replaced, and you could upgrade to your, next version of your RISC-V processor is something we're definitely interested in.
So it's interesting you mentioned that. I happen to have it's a Raspberry Pi 4 CM, but it is on a little carrier board to make it Pinout compatible with the NVIDIA Jetson stuff. And this is actually for putting various devices in a new device called a Turing Pi 2, which I did a review of over on Hackaday. It's a really interesting concept. And what I really wish is that more people would get on board with a single pinout, whether it be, the NVIDIA Jetson pinout or something from Raspberry Pi, or even something from you guys. I don't care who comes up with it. But there's no reason why this laptop that you guys are putting together would need to be limited to a RISC-V processor. Right. If somebody wanted to come along and build an ARM processor that uses the same pinout, that should work too. Is that something that's also kind of been rolling around in y'all's minds?
I can't say that there's been a lot of discussion around the actual pinout of the chip, but yeah, from sort of the system on module concept, I think you're hitting at the right idea there. I think it's if you check out what Framework is doing, right? Framework allows you to sort of take out the part of your motherboard that you would want to upgrade after so many years. And so if you think about that from the standpoint of, well, today you can do that with an Intel chip. Is there any reason you couldn't do it with a RISC-V chip and simply plug everything into that board? The answer is absolutely. That's something, one of the things that was really exciting in working with these folks that are building the laptop is when I mentioned to them Framework, I said, hey, I'm excited to see you guys doing this laptop. And we talked about the fact that, it's only going to have 4 cores. It's only going to have 16 gigs of RAM. So we're not talking about a rocket ship just yet. But the first thing I said to them was, would you be interested in talking to companies like System 76 and Framework? And their answer was yes, because that's sort of what RISC-V is about. If they wanted to get into generating a proprietary system that only they could buy into, they can do that today with Intel and ARM. But with RISC-V, they can work with System 76, work with Framework, sort of start raising the bar for what we can do with laptops in a way that they couldn't before. And I was really excited to hear that. I sort of tried to pitch the idea, being an open source person, tried to pitch the idea of, if you opened up your CAD files and opened up your BOM, it would be easier for folks to build stuff. And I just did it as sort of a nod in the right direction, assuming I would not get any traction there. But I have actually seen traction. So I've been chatting with them about, what would go into that? How would they be able to do that? Because obviously they're working with vendors, so they have to check all their boxes and make sure that they're not stepping on anyone's toes. But they were immediately interested because they realized that, we're not talking about competition, right? Someone who goes out and buys this laptop is not going to go out and buy a Framework laptop. Those are two different concerns. People are solving different problems with those things. Just like if they were to go buy a System 76 laptop, it's a different concern. And so by enabling all of these laptop manufacturers to build with RISC-V hardware, they're opening up the door for, well, it doesn't have to be RISC-V. Really, any chip can be sort of picked and placed in that way. And I think it would be a great, personally, that's something I'd love to see. I'd love to stop, buying a new laptop. And luckily, I have kids that I can recycle my laptops to. But for those who don't, you end up with older laptops that are pretty much not serviceable. And I'd love to see that change.
Yeah. So I first off, I would love to see somebody from RISC-V have a conversation with the Turing machine guys who are the ones building the Turing Pi 2. I think that would be cool to be able to put a RISC-V chip in with the other ARM chips on one of those.
Yeah, absolutely.
Also, if you guys want to send me one of these laptops, I'll be glad to do a review on it.
Excellent. As you would imagine, we've gotten a few of those.
Right. There's the Turing Pi V2. It's a neat idea. It's you can put 4 different essentially system on a chip, system on module boards on one. and play with Kubernetes or what have you.
Right.
When I first read about the laptop that is going to be RISC-V, I was reading the article, and then I got to the end of it, and they said, "Oh, by the way, this is also an NFT." And I'm like, "Is this actually legit?" Because I'm at the point now to where anytime somebody talks about NFTs or that side of crypto, it's just like, I just don't know about this.
You're immediately suspicious. No, I mean, you have to think about it this way. This is the first laptop that anyone's even thought about building for RISC-V. So the company involved in doing this is obviously going to be something a little different. You're not going to see it's not going to look like a Lenovo. That's not what the process you're going to be going through. And you can sort of think about this as a prototype in and of itself, right? I think the number of units we're talking about getting up to, if possible, would be 10,000. So we're not talking about huge numbers here. So when you're talking about that small amount of numbers, there's going to be a lot of marketing buzz around it and different ways to try and spin the laptop to make it interesting. What I can tell you is at the end of the day, when this actually starts shipping and you go and look at the specs, it's going to be pretty straightforward. You're going to look at it and think, okay, yeah, this is a laptop that I probably want to boot Linux on, and I probably want to pick one of the Linux distros that gives me, more bang for my buck in terms of performance.
All right, and we're getting close to running out of time, but I've got to ask about Horse Creek. This is kind of follows the Intel naming scheme for their processors, but this is something different. Give us the quick version of this.
Yeah, absolutely. So, I mean, being an alum from Intel and having worked on RISC-V even when I was at Intel, I'm really excited about this because it does show that Intel is changing gears. They're shifting the direction their ship is sailing, and that's going to take a while. But when it does shift, I think when you start seeing a company of that size being able to put their weight behind generating a platform, I think you're going to see something really impressive. Because one of the problems I'm trying to solve today is, how do I get hardware into the hands of distros, right? Linux distros. That's going to be a key to RISC-V software success. We need to make sure that folks from Debian, from Ubuntu, from SUSE, from Red Hat, all of these Linux distros need to have hardware to actually do their job. And while it's a lot of fun working with some of the smaller companies, folks like BeagleBoard and this new laptop company, it's fun working with them, and we get to create some really interesting products. That's not what these distros need. They need something that's much more that looks like a server. And I can tell you from having worked on these platforms before, it is a huge lift, but it's not a huge lift for Intel. That's something they do every day. So if anyone can rock the boat, it's them. They can come out with something that I can then go hand off to folks over at OpenSUSE and at Fedora, and you'll see sort of the sea change will begin when the software starts natively compiling on RISC-V, and suddenly you can go off, and when you're hitting your download page for your software, the options are Intel, probably M2 processors for Mac, and then RISC-V. I think when you start seeing that, it'll be because of companies like Intel that have put their weight behind producing platforms that software engineers can use to compile their code.
I want to ask some more future questions, but first, I want to tell us about Club TWiT. Club TWiT is great. It's another way to support our network. As a member, you get access to ad-free versions of all the shows on TWiT, as well as other great benefits as a bonus TWiT Plus feed that includes footage and discussions that didn't make the final show edit, as well as bonus shows we've started, such as the Giz Fizz, Ask Me Anything, and Fireside Chats, and Jonathan's own show on the weekends. With your favorite TWiT guests and co-hosts. As weekly FLOSS listeners, you may also be interested in, now I'm getting to it, checking out the Untitled Linux show. That's Jonathan's show. We're doing this out of order. That's available only, this is important, to Club TWiT members. So sign up for Club TWiT for just $7 a month. Head over to twit.tv/clubtwit and join today. We thank you for your support. So getting back on my small screen that I'm unaccustomed to, so I can bring our images back up front. I want to ask about the far future here, and I asked this with this perspective. I started covering as a journalist the chip business in the 80s, right? And this is when RISC first showed up as a topic, reduced instruction set computing. We haven't even visited that acronym yet. And the big players were Motorola versus Intel and AMD and a few others that were, and Spark had come along. Spark International was a phone that rang on my desk for a while because I was working for Sun as an outside operation at the time, as an outside contributor, and it had the complete disinterest of all of the companies who were working on Spark in cooperating with each other. So there's two things going on here that I'm observing. One is the Linux Foundation has done a really good job with all of its operations of pulling together these giant companies, which of course frightens a lot of people, saying, oh, the giant companies are running everything. And you've covered a little bit how you keep that from happening, because kind of basic things on engineers that are close to whatever needs to be done. But the important thing to me about covering this in the 80s is who won? ARM did. ARM was Acorn back then, and nobody cared about them, right? They had nothing going on. But in the A in ARM stands for Acorn, and they're sort of the prevailing one at this point. So where is RISC-V, or whatever numeral it will have, in the far future, in this game, whatever this game is? Because I mean, part of what I want to see is this complete modularity you covered a few minutes ago, because I think that's so much better an approach to everything than the complete verticalized world that we seem to be living in now, where Apple especially, they're from Silicon on up. But I've even heard rumors from no less than an Apple genius, who I will not identify, saying, no, we want to be based, we want this thing to be more modular. We want these things to be more fixable. And not just by us, but by anybody, because we want to, we want like a normal marketplace working here. So where do you see this going? What's the evolutionary path?
No, I think, so you asked me a similar question last time about, where I saw RISC-V going. And I think my answer back then was, we're trying to define how does one do open source when it comes to an instruction set architecture, because that problem is still to be solved, and we're in the process of solving it. I think that still stands. I think that is still a problem we're solving. And, in our day-to-day at RISC-V International, at the Linux Foundation, those are the problems we're addressing of, as we layer on top of RISC-V, each layer requires some oversight. How do we do that in an open source manner? And what does that mean? Because you can't just copy and paste what we did for Linux. It's not directly relatable. There are different problems to be solved and different concerns that need to be addressed. So that's still happening. But I think, you touched on modularity. What I think the modularity and what the flexibility of RISC-V is going to get is, first, it's going to encourage innovation. It's going to allow folks to go off and create custom extensions where in the past they weren't able to. And that's going to start to enable aspects of computing that we haven't thought about yet. So that's sort of piece number one. Piece number two, I think, is the cost savings that's sort of inherent in all of that isn't really there yet, but that I think will be at the heart of what RISC-V gets us. Because you're no longer, it's not just the licensing cost, right? It's not just that, but it's the R&D costs behind spinning something up. So if you think about, let's say I, as a human being in the 80s, wanted to create an operating system, what would be my chances for success? And now let's take it forward to today, and I want to make my own operating system based on Ubuntu. What are my chances for success? I think that you're starting to see the cost behind doing something like that came down hugely because of the community effort around rising the bar for everybody. Everybody gets to sort of sit on the back of Debian, so we all get to go a lot further. I think the same thing is going to happen in hardware. You're going to start to see that rising tide happen, and that's going to drive cost down, because suddenly you're not trying to spin something from scratch. It's not your concern what the opcode looks like. They've already figured out the opcodes. They've already figured out how you can layer your custom extension on top of the base processor, all you have to do as a company is concentrate on your custom extension. And so even though that veers a little away from the standardization I talked about, what it does veer toward is that innovation, the ability to do something completely off the beaten trail that no one else is interested in because they don't want to standardize around it. But if you can hit on something interesting, something different, that'll change the industry. And I think that's really what we have to look forward to. And yeah, I'm excited to be part of that.
All right, so I've got to jump in with a totally different question, and I've kind of got a reputation on Floss of being the one that asks the really technical questions, and I'm going to continue to live up to that, I think. RET bleed, which is one of these speculative execution problems. It's the idea that in Intel and AMD and even ARM processors, you can manipulate the processor to where it will speculatively execute out in a direction, and then, execution catches up with it. It rolls it back so that it does the right thing, but it changes the way, essentially the cache. It changes what's sitting in cache. And then if you're really clever about it, you can figure out those changes and read things from memory that you're not supposed to be able to read. That's the 30-second explanation of speculative execution problems.
That was a good high level right there.
There you go. Is this a problem in RISC-V? Did RISC-V get hit by RET bleed or any of these others? Or is it just architectured in such a way that it's not an issue?
So I'll say no with a caveat. It's not an issue, but with a caveat. So one of the great things, so I was actually at Intel when Spectre and Meltdown happened. So this is a subject that I've listened to and contributed in many conversations around. RISC-V has the sort of the benefit of hindsight. So when RISC-V was designed, they already had this concept of, speculative execution, and folks were already trying to poke holes in it. That was common. So that's kind of the first piece that gives RISC-V a little bit of an edge. It's the second mover principle, the idea that, stuff has already come before us. We cannot make the same mistakes. The other key behind RISC-V that sort of, that gives us an edge here, RISC-V, especially RISC-V International, but as a group, what we're doing is not implementation. We don't build caches. We build, simple implementation caches that are examples, but we don't fully flush out caches. What we do is we create interfaces that allow implementers to go off and create those caches. So what we can do is provide them with guidance, given what we know about the history of speculative execution, such that they can go off and build products that are less likely to have issues. Because if you think about it, as soon as you start building products, you're building bugs. The second you start producing something, whether it be a hardware product or a software product, you're engaged in building bugs. So all you can really do is set folks up for success and then take the feedback that you get and implement that in your interfaces. And that's what we're doing. We're making flexible interfaces so that folks can go off and build their caches, and then keeping those interfaces up to date such that the next generation of RISC-V will be able to take into account anything we've learned in the interim. So the answer is no, but with those caveats. I'm sure you can go out there and find an implementation that is probably susceptible to this. However, moving forward, we've already integrated in these concepts into how do we keep it from happening again in the future.
So it's actually going to be a kind of a very different approach that things like the kernel is going to have to take to it. Because in the kernel, you can simply say, all right, anything from Intel from this generation to this generation, we know is going to have the RET bleed problem. Anything after it is not. Whereas with RISC-V based architecture, it's going to have to be essentially product by product.
Well, we are going to align around two concepts, profiles and platforms. We don't have time to talk about that in 3 minutes, but the concept being you can think about things like ARM v8 as being our profile. So we will have a sort of line in the sand that folks can go, okay, if you comply with, RV22, RV22A has these features, and maybe one of those features might be vulnerable against some attack. So we will have ways to draw a line in the sands. We want to make software people's lives as easy as possible, but we also want to make it easier for innovators and implementers to create unique products. So it will be a balance somewhere between those two areas.
So this has to be almost a record setter for how fast an hour can go. I think the number of seconds and minutes in it is no different, but the amount of information it contained is enormous, and this has been great. We always close with a couple of questions. Somebody's there's the back channel.
I knew I was going to hear about NFTs when I saw that on the laptop page. I figured I was going to be in interviews for several years where that still came up.
Yeah, it happens.
I appreciate them keeping my life interesting. I don't want things to be boring. So is there anything that we haven't asked that we should have asked that you'd love to answer in any case? Yeah, I think so. What the question I get asked the most from people are just, when am I going to be able to buy the next RISC-V insert thing here? We have a program called the Developer Board program that I highly recommend your audience go take a look at. So as hardware becomes available, RISC-V International is going to make that hardware available to engineers to do interesting projects. It's a fund that we've gotten from the board of directors down, and the goal is to encourage folks to work on RISC-V hardware because we know it's hard to get a hold of. So I would highly encourage folks to go take a look at that. We do have a limited supply of boards. Like whenever we purchase, we are only allowed to purchase so many. So we have to be kind of choosy about, which projects we give the green light to. But it's a great way for someone to get involved in RISC-V, get hardware on their desk, and start playing around with it. I think the feedback loop too to the community is really valuable because the work that's done gets posted publicly. We require that it be open source. We require that you give us feedback. And so we're actually seeding both engineers who want to do work and the community who want to see work being done and be able to build off that work. So it's a really exciting program. I would recommend folks go out and take a look at it.
So for the last two, our standard questions, what are your favorite text editor and scripting language? I know you answered it before, but maybe that's changed. I don't know.
No, it hasn't. It's still Vim. Vim is unfortunately my gift from being an engineer in a former life, so it's still my text editor of choice. And I do have to, I think Python was my answer before, and I'd have to stick with Python if I'm still choosing a language. Though I have to say that those skills are getting dustier and dustier every time you ask me that question. So,
well, I expect that given the pace of things happening with RISC-V, we'll have you back. We always say we'll have you back. You're living proof that we do that. We actually have people back.
It's great to be here.
So thanks so much for being on.
Absolutely.
Yeah. So Jonathan. A lot of stuff on this show.
Yes. It sounds like I did not successfully talk myself into a free laptop, which, I'm kind of bummed about. That works every once in a while.
Well, maybe one of our listeners is privy to some of that. And
there you go.
Somebody with one of the OEMs out there working on this can help you out.
Yeah, no, it's pretty cool. I've not gotten to get my hands on any RISC-V hardware yet, so I need to pick up one of these developer boards just to be able to play with it and say that I have. But yeah, it's a very cool idea, and I'm excited that they're doing some of these different things like the vector extensions. So you could feasibly put together a GPU using RISC-V, which then leads you to the idea of an open source GPU, which is it's been the dream for certain people for the longest time. They're just kind of marching forward with all these things that you would expect and require to have from a modern CPU. And you already see RISC-V. You already see RISC-V in things. It's just not in places where you actually see it. So like there are some hard drive manufacturers that put RISC-V in their stuff. Intel uses RISC-V internally in some places in your CPUs. It's just none of it are in places that you have any visibility. I guess I'm kind of looking forward to the first time that somebody ships something that is obviously running a RISC-V CPU in it. Whether that be a phone or, the laptop, but that's a limited run and kind of a unicorn. One of these days, HP is going to make their HP Dev 1 and put a RISC chip in it instead of AMD. And I kind of think that that's when RISC-V is really going to make the jump from a very niche, certain group of engineers know about it to maybe a little a little wider public knowledge about it, and that'll be fun.
Well, one of the things that intrigued me is that when he said about, what succeeds in the long run is going to be something that's not anywhere else that is too tempting. I don't think he said this exactly, but that was my take on it. That there'll be something. Maybe it's this vector thing, and roll your own GPU. That would be very cool. And there's, I expect it'll succeed. I love the energy in it, and I think that the energy says a lot. And the fact that there are in fact big companies in it that, while they don't have their fingers on the scale exactly of the development of it, are interested enough in it to make something happen. So I'm encouraged about that.
Yeah, it's always fun. So we are all the time just throwing things at the wall and trying to see what sticks. And it's always neat to see something kind of radically new start to work and start to really gain momentum. And I feel like that's where we're at with RISC-V. It's something totally different from anything we have in the CPU/GPU world right now. And it's getting to the point of getting critical mass and getting some momentum. And so I think we could be the RISC-V guys could be in for a really interesting, say, next 5 years. Could be quite the ride.
Yeah. And so we'll stay on that horse along with Stephano. I have to let you know, next week, really interesting show. Maxie Reynolds of Subsea Cloud is going to be on. This is cloud running under the ocean, like the fiber you're probably watching right now also does, but putting like a data center under the water is a really interesting thought. So that's coming up next week, Maxie Reynolds. In the meantime, what do you got to plug there, Jonathan?
All right, hackaday.com. Make sure every Friday morning, catch my security column there and the occasional review and coverage of other things from me. And then you already mentioned it, but get on Club TWiT and go subscribe to the Untitled Linux Show. And we have a lot of fun there, and make sure to come join us.
Yeah, and as is my custom, I did things a little bit out of order, but that's cool. Next week again, Maxie Reynolds and Subsea Cloud. I'm Doc Searls. We will see you then.
Did you spend a lot of money on your brand new smartphone and then you look at the pictures on Facebook or Instagram and you're like, what in the world happened to that photo? Yes, you have. I know. It happens to all of us. Well, you need to check out my show, Hands On Photography, where I'm going to walk you through simple tips and tricks that are going to help make you get the most out of your smartphone camera or your DSLR or mirrorless, whatever you have. And those shots are going to look so much better. I promise you. So make sure you're tuning in to twit.tv/hop for Hands On Photography to find out more.